And hello students, this is a help for homework 5b here. This is out of chapter 5 and it's the second part of the chapter. And we're going to go through this first video. I'm going to try to get through 533 here. Okay, we're going to get through this bunch here. I'll release it, post it, get an email out to you here. Okay, so the first questions that we have here have to do with Bernoulli and binomial. Okay, we're going to get into the Poisson. I will do a Poisson here is 533. Now, just as a guidance for doing these homeworks, when you read the book, they've kept it fairly straightforward. So they've shown you the basic examples, and then they show you the formula to use out of Excel most of the time, and they explain how to use it. They're basically leading you to the problems. This is more of a breadth rather than depth kind of approach, which is great. This is why I like the book. You're going to get a sample of looking at a lot of different things in here. But that's the first piece of guidance I would offer you is, in a way, you need to find out in the problems, these problems here, these 526 through 33, or any of the ones that we'll eventually do anyway here, or in other modules or other weeks that we do this. You have to find out somewhat where to place numbers, okay? So they break it down, they give you equations, but then they break it down and they give you an example with a formula out of Excel generally, okay? And then through 526 through 531, you should be able to get a really nice feel of the binomial distribution formula or function out of Excel. And after you've had this much practice, you should be pros with it, and you should be able to apply it fairly well. Once you see them in mass, you probably see it that way. And hopefully you'll see the way that this was all presented because it's repetitive here, okay? Now just a couple little tricks or a couple little things that you have to watch out while you do that. So let's take a look at 526. All right, so we come in here, a major application of analytics in marketing determination, customer retention. Okay, suppose that the probability of a long distance carrier's customer leaving for another carrier for 1 month is, for 1 month to the next, is 0.16. Okay, so these are algorithmic problems. Each of you will get a different set of numbers in here. Okay, so every time I do this, I get a different set of numbers. What distribution models the retention of individual customer? What distribution models the retention of an individual customer? What is the expected value and standard deviation? Okay, so I'm going to flip over to the book here. Here's our book. Okay, so here is, back up a page, we're going to talk about the Bernoulli distribution. Okay, and really that's basically, the Bernoulli is pass-fail tests. Okay, so there's either a 0 or a 1. Okay, it's pass-fail, kind of like positive negative tests right now on all kinds of medical tests that are going on out there. You might say that there's a parameter. Okay, so if you're producing something on a production line, you might limit the number of knots in a 2x4x10 that's going to go to Lowe's or Home Depot, and say that they have different grades, and one of the grades might only allow 4 knots per 10 foot, like this in this board. Okay, and it's a pass or fail if it has if it has 4 or fewer. Okay, so 4 or fewer knots, it's acceptable. Okay, and that's at a certain grade level usually, only with a grade. Okay, so that's 2x4x10s. Okay, and it either has fewer than 4 or 4 or fewer, or greater than 4. Greater than 4 gets into a different grade. Maybe it goes to a different store. They just label it as something else. Okay, so get, it can have, the actual item or your actual target of interest here. It could have other numbers involved with it. This is just simply a pass-fail test on it. Okay, that happens often in operations, that you have a pass-fail by counting the number of things. Okay. All right, so let's go back and take a look at the problem here. Bernoulli problems. Okay, so Bernoulli is a 1 or 0. I'm going to pass to the next page here. That just tells you, this page just tells you that what I just said. Okay, and it's simply that there is some kind of probability for one outcome, and there's the inverse, or the complement rather, the complement of that probability for the other thing to happen. Okay, so what do we mean by that? All right, so if you flip a coin, it's a fair coin. Generally, it's about probability of a heads. Okay, is equal to 50. And so the probability of a knot head, or i.e. a tail, okay, we'll call that probability of tail, not head. The other thing that happens is 50. Okay. So if you're playing with some kind of, could be, it's good to think about flipping a coin, but the coin doesn't always necessarily have to be completely fair, so to speak. Okay. So you could do a couple of things. You could make a coin that is split down the middle, and there's one heavier metal, a denser metal on one side than the other. Let's say that causes it to have a different behavior. Okay, so let's say the heads side is weighted. So we would assume, I'm not sure if this is true or not, but we'd assume that it would land heads down or get a tails more often. And let's say that's now it's a 70%, 30%. Okay, so the outcomes are completely independent of each other. Okay, from one toss to another. And the outcomes here, the probabilities have to add up to 1. Okay, so the 0.3 and 0.7 would be 1. And then 0.5 and 0.5 would be 1, like that. Okay. All right. So they're exclusive of each other. So those are the three things. They're independent from test to test. They're exclusive from each other. And the probability of every outcome. No, in this case, we have a die, or I'm sorry, we have a coin. But if we're thinking about a die has 6 sides to it, of course, right? There's a die. All right. So that has a different thing. That has 6 possible outcomes with a uniform distribution. Okay. It's equally likely that any face will show up. Okay. A fair coin, let's call it equally likely that either get a heads or tails. Okay, so you could get, this is what you want to keep in mind as we start down this path. When you think about Bernoulli, you have to think about those three conditions, and you have to think about the fact that there's a white, there's a black or white, or there's a 0, 1, true, false, positive, negative outcome. It's one of two different things, or we could call it dichotomous. That'd be another way to use it. That's often used. It's dichotomous. There's only 2 things that can happen. All right, so it's kind of good to think about this as a coin, and we could vary it somehow. That the outcome we could change the probability of it coming out at will. Okay, so we change the parameters of a coin. It's not a bad way to look at it. So when you start looking around, so basically you're going to start looking around for examples. That's a pair of glasses. All right, so you're going to be looking around for things that are dichotomous to apply Bernoulli. Okay, and then we move into the binomial. Okay, so the binomial is simply a repeat of binomial. Okay, so binomial is just a repeat of this some number of times. Okay, so all that means is you have a distribution. We're going to look at a frequency distribution of what we can expect as an outcome. Okay, and we're going to call it the probability mass function. Okay, so in discrete, okay, so we're talking about discrete, we can watch one happen, we repeat the same experiment or event, and we look at what comes out again. They're discrete. We're just not continuous, where we're measuring temperature continually over the period of the day of a batch of, I don't know, chocolate we're making. Okay, so it's discrete outcomes. All right, and so what we're mapping here are let's say that we're going to flip a coin 100 times. We're going to map the likelihood of outcomes. Okay, and that could range from, and then we're going to go by heads. Okay, we're going to say how many heads did we get out of flipping 100 times. It could go from 0 to 100. We could get 100 tails in a row. That means we had 0 heads, or we get 100 heads in a row. Now, I think you'd probably start wondering what's going on if you're flipping a coin and you get 100 heads in a row, but it can happen. Statistically, it's not 0. Okay, and so what's the most likely outcome of it? Well, we would say if 50-50, it would say about 50%, or 50 out of the 100. Okay, somewhere we're gonna think that most frequently we're gonna get that. If we flip 100 coins 100 times, okay, that's what we're saying. If we flip 100 coins, flip a coin 100 times, and we do that 100 times, okay, what we're gonna find out, the outcome is gonna be generally very high, around 50. Okay, and if we count down to 49 and all the way down here, that if we plot this, okay, so it's discrete. We can have we get discrete. We have a number of times that one of these things happened. It gradually decreases here, and you will see, excuse me, you will see that the profile of this looks like a normal distribution. Okay, again, it's there's central tendency here, centrally located. Our average is going to be around here. If 100 times we flip a coin 100 times, the average of those 100 times is going to be 50, about 50, somewhere around there. Okay. Now, immediately, let's take a look at what if we have an outcome that does not have a 50-50. Let's have we have this imbalanced coin here, and we could just program it so it would flip, change it over so that we only get heads 30% of the time. What would happen to this profile? If only 3 out of 10 times on average, okay, we get heads, okay, it says that with that kind of coin, it would look like this. It was like around the 30 out of 100 times that we do this is going to be where the highest frequency is going to be. It's going to be centered around this. It's now what's happened to this. This is now right skewed, okay? Most of the time it's going to be around 30. Okay, so that's in a bucket, in a real nutshell here. That is a nice wrap up of how to think about Bernoulli and binomial. Is that first of all, it has a 1 or 0 or 0 1 outcome, pass fail outcome, and the curves, as you'll see, is if it's 30% likely to get the heads, then the curve, if we count this up, we flip it 100 times, many times we do this, we're going to see that most of the time it's going to come out around 30 if that is the relative difference in the probabilities of the outcomes. Okay, so we can come up with a mean. Okay, so the mean is going to be that p. That's all it is, 30 over 100. Okay, for instance. Okay, but what is our variance? A variance, okay, is going to be p times 1 minus p. Its complement. So then you have to take the square root of that if you want the standard deviation. Now I've brought over 526, problem 526, but I'm going to go into something here to understand how this binomial works. Entering into the topic by trying to solve the problem is maybe not as revealing as using the binomial function within Excel to understand what we're even talking about as far as Bernoulli and binomial. Okay, so first I'm going to get out. This is actually a Bernoulli problem that we have here, but I'm going to show you what happens when we talk about the binomial that we're going to get into in 527 and such. But you're generally interested in binomial anyway. Bernoulli on its own is what it is, but generally we're looking at the occurrence of something happening or not happening over a number of tries. As I mentioned before, that we have things going on now with the virus and test kits and things like that. You're trying to get a black and white answer to that. Okay, so the idea behind binomials that you've run Bernoulli some number of times. And I've set this up to say, hey, let's run something. It's a black and white test. Let's flip a coin 20 times, a fair coin. Okay, so we're going to flip it 20 times. And what we're plotting is, what's the probability of getting 0 heads? What's the probability of getting 20 tails in a row? What's the probability of getting not in a row? I'm sorry, not in a row, just at all. What's the probability of getting only one head? What's the probability of 2 head? And this is when we're using the binomial. This is very common in business. Okay, so you have these black and white tests. You figure out what the probability of the outcome is of the outcome of interest as it is. Okay, so we're going to use the binomial function here, which is discussed in the book, but we'll run it through a few times. If you see it move fast, then why is that working? Because I didn't put my equal sign in. Binomial.dist. Okay, it's better to show it dynamically how this works. Okay, so the number of outcomes, the number underscore s in this formula here is going to be this. Okay, so we're going to run a test. It has some probability of an outcome, and this is the number of, say, successes or identified of the outcomes of interest that we're looking at. The number of trials will be 20. Okay, the probability, what's the probability for this? A fair coin is going to be 50%. And the last switch in this formula tells you whether you want the unique probability mass function for this one outcome or the cumulative, and we want to have the individual. So we're going to put in a false here. Okay, so this is the probability mass function that you see down there. Okay, all right, so we hit enter. Okay, so there's a minuscule probability that you're going to flip a coin 20 times and have it come up with all tails. It's 9.5 times 10 to the minus 7, which is something on the order, I think, of 10 to the minus 10 in a million. Okay, or 10 in 10 million. Okay, so that's how small that is. You have to sit around there and flip it 10 million times. You might get 10 times. You're going to get all tails. All right. Now, if you think about it, it's symmetric because on the other end of the spectrum that we're using here, we're saying we're going to get all heads versus all tails, right? So we're going to expect if we run this equation down, okay, first thing I need to do is make sure that I lock down my key reference here, my key data reference. All right. Okay, so if I drag this down, you're going to see that 20 heads is equally likely or unlikely to happen. Okay, so let's do a quick plot of this. All right, this is really needed to understand what we're getting into here. Okay, so I'm going to do a quick let them tell me what kind of dial. That's great. I'm going to go along with that. Okay, so here's a nice little graph of this. Okay, and this shows a fair coin. Okay, but if we just think of the coin in approaching all these other dichotomous outcomes that are out there in business, you're always doing these pass-fail tests and whatever. Okay, what if it was only 30% likely to be heads and 70% likely to be tails? So let's see how that curve changes here. Okay, so what you can see, essentially, the central tendency is going to say that, excuse me, out of the around 10 or 11, the peak of the curve occurs right in the middle. Okay, so this is saying that out of 20 times, you're going to say that about 10 times out of that, you're going to get a heads, or 11 times out of that, you're going to get a heads. You can see that that reflects that on average, if you keep doing this, if you keep flipping a coin 20 times, you're going to keep seeing that you're going to pretty much get the average more frequently or more likely, and then you're going to get these strange edge numbers very infrequently. That's what this graph shows. Getting a 1, it doesn't show the 0. I don't know why. Excuse me. Maybe I didn't get that one. All the way up to 21. Okay, I think it actually assigned its own numbers because 1 is actually 0 here. That's how that works. So I can see what went through 1 through 21. Okay, so we locked that down. What happened here? Let's change this to number of trials. We lost the. Let me just type the whole thing in again. Is equal to the binom.distribution. And we're going to put in here, this is our outcomes, number of trials again. Probability is now only 0.30. What if we have an uneven coin here, or some other kind of test? And then finally, we're going to put in false. Okay. All right. Now let's see what happens to our curve. Always remember to lock down your cells. Okay. And now what you can see is that it's skewed right or positive skewed. The lobe is down here at the lower regions of, it's more likely we're going to get something in the, let's see, the 6, this would be 5, 6, 7 actually. These are arbitrary numbers that Excel assigned. It did not use these as labels for the bars on the column chart, columns on the column chart. Okay, so you can see it skewed things. It's more likely we're going to get fewer heads, right? We're going to have fewer heads down here. There's a number of heads when we do it. Okay, so that's just to get a feel how the binomial works. It's better to see. It's almost like a movie. It's better to see it move like this before we try to just ratchet it down and look at specific examples here. Okay, so let's take a look at this problem here. A major application of analytics in marketing is determining customer retention. Okay, so if they stick. Suppose that the probability of a long-distance carrier's customer leaving for another carrier from 1 month to the next is 16%. Okay, so the walkaway rate is going to be 16% in this problem. Okay, so let's put that up here in a key area. Walkaway rate is going to be 0.16, but we're really interested in retention rate, so it's going to be the complement of that, right? What distribution model for what distribution models the retention of an individual customer? Okay, I'm going with Bernoulli. Okay, now we'll calculate the expected value. And the expected value would be, this is the walkaway rate. It's going to be equal to 1 minus the walkaway rate is the retention. It's just simply that, 0.84. Okay, and then finally, I think it's asking us for the standard deviation. Standard deviation. What is that going to be equal to? If you refer to the book, standard deviation would be, well, the variance is p times 1 minus p. Okay, so that's going to be equal to p times 1 minus itself. Okay, all right, and I'm just going to let that hit enter here. Okay, but we need to take the square root of that. Okay, so we'll do the SRT of the entire thing. And square root would be 0.367. Okay, and that pretty much tidies everything up from there. We'll go now on to 527. So here we have our 527. Call center data shows that in a sample of 40 individuals, 17 had prior call center experience. Okay, so it's either 1 or 0. They either do or they do not have call center experience. And the observed frequency is going to be 17 out of 40. That's going to be our probability there that someone that we have come in is going to have had previous call experience. We assume that the probability that any potential hire will also have experience with the probability of that. What is probability that among 10 potential hires, more than half of them will have experience? Define the parameters for this distribution based on the data. Okay, so we're going to go into the binomial. I brought this back with us. I brought this over with me from 526 because it's just a reminder of what we're doing here is that we're doing something, we're going to try something 20 times, and we know that the probability of heads, in this case, let's say heads is a 1 outcome versus a 0 where it's a tails, all right? Okay, and so there's this probability distribution that we have here that resembles the normal distribution, whether it be skewed or not, all right? Okay, so that's what the binomial is going to look like. So let's go in here with the binomial. Let's type some numbers in here. So the probability of a true or a correct probability is going to be equal to 17 over 40. Okay, so it's basically a 42.5% chance that when we get somebody that they're going to actually have this experience. Okay, 0.425. And we just assume that applies across the board here. It's constant. All right, so now let's remember what we had to do here. Is we want to know if we're going to get, if we take 10, okay, so the number of trials we're going to have is 10. We're going to pick 10 hires. What's the likelihood of more than half of them will have experience? So now we're going to have to see the other form using true inside the binomial equals binomial.dist. Okay. Okay, so the way that this formula works, okay, and the way that for this type of problem is it's going to say the binomial dist of this number. Okay, so we want to know the way that the binomial works is from the left, just like other things that we were doing with the normal distribution. Is when we use the cumulative form, if we use the cumulative form of the binomial function, that's going to say what's the probability of getting like 0 heads, 1 heads, and 2 heads, and 3 heads. What's the probability of getting up to and including 3 heads? Okay, so that's what cumulative means. It means up, including everything from some point of interest below, but this problem wants 10. It wants to know, will we get more than half? More than half would be 6 or above. Okay. All right. So it's testing our attention and our acumen here to see that we're paying attention. And really, we're going to end up having to do the distribution of 5. Okay. So we want to know what's the probability of picking 1 through 5. Okay. That out of 10, 1 through 5 of these candidates have experience at only 1 through 5. Not in, so we don't have 6, not the probability of 7, 8, 9, 10. Okay, so at 5 out of the n, which is 10. Okay, the probability of up to and including 5, the probability is 0.425. But this time, see, we want to use true, and that turns it into the cumulative distribution function. It's going to include the whether when we pick these or we sample these candidates that come in, okay, we're saying what's the probability out of 10? We're going to get 0, 1, 2, 3, or 5. 1, 2, 3, 4, or 5. Okay. All right. So the probability of getting only up to 5 is this much. And then we're going to have to take 1 minus that. Okay. So we're going to take 1 minus, because everything is inside the formula here, we could just do 1 minus without any extra parentheses. And so the probability should be 0.211, or 21.1%, that out of 10, you're going to get 6, 7, 8, 9, or 10. Okay, so to detail that a little bit more, in our trials here, we're going to say 10. Okay, so let's ignore all of this. Delete. This is a good thing to do with when you're looking at these problems is let's tease out what the behavior of this really is. Okay, so we're going to basically copy the same binomial function in here. Okay, the same binomial function we're going to put over here. Okay, as I actually have to do it. All right, so is because I only copied over the values, I didn't come over the equation, binomial. This is almost like the movie version or a teased out version of what we're talking about. You have to see it in context to understand what we just calculated. All right, so the first thing it is, we're going to give it B4. Okay, so B4 is underneath what I'm writing right now, so I have to actually type it in. Okay, and the number of trials is going to be equal to this cell here. We're going to have to change that to 10. Okay, and the probability is over here. We have that. And what we want to do is now we're going to put in true. Okay, we'll make the function perform a certain way. I got to change this to 10. Okay, so we have 10 trials. Here's our probability over here. Okay, we calculated that. For the problem, we actually calculated what the problem was asking for, but let's look at what it's talking about here. Okay, so the probability of taking 10 people in and none of them having any experience is going to be that. Okay, I'm going to lock this down before I drag it. Okay, so now I'm going to drag the formula down here. What did I miss? B4. Oh, I forgot to do this one also. There we go. I have to do 2 here. All right, let's try that. That should work. Okay. All right, I'm going to bump this up like this. Let's go to 3 decimals. I think the problem asks for 3 decimals for this problem right there. I think the answer here, they want it in 3 decimals. All right, so we'll be kind to ourselves. We'll use Excel, knock it down, and we'll just type that in. Okay. All right, so if we look at the probability here, this is now going to look at like a different thing. We're going to do, when we do this graph here, okay, we're going to take a recommended chart. Sure, we'll take that. See, we did the cumulative form now. All right, we did the cumulative form of the equation of the binomial, and what it does is it adds the probability of the previous one to each succession of these outcomes in here. So what we were being asked is, they wanted to know what's the probability of getting 6 or more candidates that had experience. That's what that was asking for. It wanted to know that. Okay, so if we tell you what I'm going to do, I'm going to take the same formula and I'm going to run it over here on the side. but I'm going to do it to show what the individual probabilities are here. Oh, Control Z. Something I broke. Okay. Do that one more time. Control C. I know what I did. Okay. Control V. Okay. So what we've plotted, I'll plot this as well. So I'll plot that. Insert. This is what we had before. Recommended charts. And I'm going to take it. Okay. So what we're seeing here is this guy over here, right? Okay, so the probability of getting 0 is shown on the graph here. The probability of getting 1 candidate is shown here. The probability of getting 2 candidates is shown here. Okay, the next graph that we did is just cumulative. It would take for the second slot, it would take the previous, add it to 2, it gets larger and larger. So that's why this is called an ogive curve. That technically it's called an OGIVE curve, an ogive curve. Okay, this is a normal distribution. Okay. Okay, so I wanted to show what happens. The total probability. The reason I did this was this is let me do the sum of all these. The total probability of any of these outcomes is equal to 1. That was the purpose of me running through this. And so you'll see that if we keep adding them up, we eventually come up to a probability of 1. And the reason why these both show 1 is it's an issue of decimal places. If I push that out, let's see how many decimal places I need to take that out. Yeah, not very. Okay, I don't have to go very far before it. You'll see that it's not exactly 1, whereas this should be exactly 1. Great, didn't make me a liar. Okay, we're good. Okay, so that's exactly 1. All of our probabilities are mutually exclusive. They all add up to 1. All right, that's one of our laws of what we're doing here. Okay, all right. So what we ended up having to do was when you do the cumulative. Okay, so we used the cumulative here. Ignore the 1 minus at the beginning here, but what we had to do is we actually had to use the function as it comes, and it says let's take all the probabilities of all these and add them together. I'll color that differently. All right. Okay, so these probabilities we can calculate with a binomial. We could calculate it up to this point, and then we had to subtract the 1. Okay, that gives us the remainder, the orange section there. Okay, I don't want to beleaguer the point here. I'll move on. We're going to go on to 529 now. Okay, to take a quick look at this, things should start, they begin to look familiar to you. During an 8-week period, particular mutual fund outperformed the S&P 500 27 out of 40 days. So I'm going to get into kind of a quick mode here without beleaguering points. It's the S&P 500. Okay, so it said, did a share? Yeah, mutual fund. Did it break the S&P 500? And that's just a 0 or a 1 situation there. And it said it did it in 27, that's 7 out of 40 times. Okay, so the probability is 27/40th. All right, okay. So you're going to do your binomial. Okay, so it wants to know, you have to find out what the question wants, find the probability that it would perform as well or better. Okay, so that's the tip off. Okay, so again, we're going to look at something where 40 times, which is 8 times 5, because 8 weeks times 5 days a week gives you the 40 days. And can we beat it? The next 8 weeks is the idea. Can we get that rate going over the next? What's the probability of doing that or better? Okay. So it's going to be one of these left-handed things. The same idea here, whereas if we did the entire binomial table, we'd say, what if it never broke it? All the way down to if every day it broke the S&P 500. Okay. Okay, so we have one of these tables here. We run the binomial function down here to visualize what's going on. The binomial function, we do all of these down here from 0 to 40. And right about here, it has 27. Okay, so it's saying, what if it gets 27 or better? Okay, so what we have to remember is the binomial function in its cumulative form, when we do the true at the end, okay, it's summing events. It's summing from the beginning, though. It sums from 0, 1, 2, 3, 4, 5, 6, all the way up to 26. Okay? So we want to take 1 minus the cumulative probability that it could have been 0, 1, 2, 3, anything up to 26. All right? So you're going to run that out something like this. 2640 probability is 27/40 with true. Okay, and work out the rest of the problem. I don't know. I'm not sure. Sometimes these feed you another problem after you answer one. It starts feeding down, but that'll get you almost all the way there. Okay, so let's go on to 530. See what's unique about that. Okay, so this has a little bit of a different twist. I would actually give it a shot before you listen to the rest of this, right? Try to see if you can figure out what the parameters are calling for here for you to do. Okay, so I'll just tell you, why don't you try pausing it here? And I'm going to keep going and see if you came up with the same thing. Okay, so this says 300 rooms. Okay, 300 rooms, and it wants to know at least 275. It wants to know 275 of 300 rooms. Okay, and we have the probability of somebody canceling as 0.07. So our rate is 0.07. Okay, so we want to know the probability of more than 200 or 276 rooms at least of, so it's greater than 250. I'm sorry, 275. So we want to have more than 275 rooms occupied. Okay. Well, there's a little bit of a different twist on this because what we can think about is what's the probability of how many? 15 rooms? 25 rooms, right? Okay. So what's the probability of it's the complement to what we're kind of being asked here is what's the probability that we had 0 cancellations and plus the probabilities of 1 or 2 and 3 all the way to 25. Okay. Okay. So it's going to be something around 25 here. I have to see what the edge here, the border conditions are, right? Okay, so if we did the binomial for that, we would just say that if we could figure out the probability that you're going to have 0 to, think about this, 300 minus 276 would leave 24. Okay, so how would we set this up in the binomial equation? It's equal to the binomial distribution formula, I'm abbreviating again, is 24. What's the probability of 24 cancellations out of 300 at 0.07 true? Okay, so that's going to lead you on. As I said, that'll get you a good start on this, and I'm not sure if it rolls into some other questions after you start answering this or not, but I'm not sure if they're ever that challenging as it is anyway. After you get the major one. Okay, so take a look at that. That's looking towards solving what that looks like. Okay, let me know if you do have problems with that. Let me know. But I think that's where you're going to be set up for that one. Okay, and now we will move on to problem 531. Okay, so for problem 531, this is a really nice real world kind of problem that we have here. If you really think about it, this is the kind of thing that we're driving at. This is why we're going to use this. Look at this question. A telephone call center where people place marketing calls to customers has a probability of success of 7% or 0.07. Find the number of calls needed to ensure that there is a probability of at least 0.91 of obtaining 9 or more successful calls. This is a real operational directive of a call center, right? If on average people are getting out of every 100 they get about 7 sales. Actually, it just says like I think it's like 7% is a connection rate. It's not even a sales. Sounds like find the number of calls. Okay, and so we want to figure out. This is the way that you actually set your directives in the company. You said, well, at a 7%, we have a real long history of knowing that about 7% of the calls get through. We need to figure out a 91% chance of getting 9 or more successful calls. Okay, so the first thing that tips us off is this is one of these right-hand problems, okay, where we want 9 or more. And so since the binomial distribution equals the sign of their function, this time we want to know that in general, we kind of start out this way. We want to know how many calls, this is the question mark, how many calls do we have to make to get 9, right? Because normally we ask, we ask the binomial function here to tell us what's the probability of getting 9 out of what. But this is what we have to figure out, 0.07, and let's just assume true at this point. This is the way that we're going to run this. But this is one of these right-hand problems, okay? So what we really have to figure out is 1 through 8, okay? All right, so we have to figure out what the probability of getting up to and including 8 and then subtracting that from 1, whatever that is that we come up with. Okay, so that's the key to the problem here. All right, so if you think about this now, this is the little trick to this. Normally we were studying, we'd say, okay, we're going to take 10 readings and see what's the probability of getting 0 hits, 1, 2, 3, etc. Okay, so that's the way we were normally setting this thing up. Okay, this is kind of neat. And again, it's very practical. It shows you how you have to torque around the Excel to make it do what you want it to do in this problem. Normally, this is what we would say, and we would end up with, we would do normal binomial.dist. Always forget that equals binomial.dist of that number. Okay, normally we'd go that number, and we'd go by the number of readings we're going to take, samples, trials, whatever it is, and then we're going to use, I'll just use 0.07 here, okay? And we're going to use a cumulative, okay? So we're going to use a cumulative form of this thing, okay? That's the way that we would normally do it. What's the probability of getting no hits out of 10 when the chances is very slim of getting one at all? See that? That's why this probability is very high. It's very high that you'll get none because your probability is very low here, okay? So this is the positive sense of the formula, okay? Now, what we need to do is flip it twice. We have to work on this 2 different ways. What we want to know is we're going to end up taking 1 minus, okay? So we need one of these types of occasions where we have 1 minus the binomial formula. And what's interesting here is now we're going to say we know we need 9, okay? And how many trials do we need when the probability is only 0.7? How many trials do we need? So this is what we're after. And so the way to do this, there's no formula in Excel to do this, but what you have to do is brute force. Okay, so we're going to brute force it. And how we do that is we're just going to exhaustively run a big list here and find it in a table. Basically, we're going to tabulate some numbers. But once again, we have to do the 1 minus, okay? And so the number that we're really seeking is 1 fewer than 9 is 8, right? Okay, remember I said the number was 8 over here, 1 through 8. We need to take care of all the outcomes where we get, well, actually it should be 0. It should be 0 to 8 positive readings out of this, and then subtract that probability from 1, okay? So now what we do is, this is the thing, this 10 is how we're looking for the 10, all right? So that's no longer part of the formula anymore, okay? So we're going to move this thing around. We're going to consider these numbers. These are now not representing the number of successes. This is going to be the number of trials, okay? So what I'm going to do is where that question mark is, I'm going to tell it to read this and say, what's the probability in 0 trials of getting this? Now I'm going to fix that. That obviously doesn't make any sense, but I have to work on this just a bit. I want to hang on to that formula, okay? So it shows we have an invalid number. It will not take 0 trials in there. And I'm going to get rid of this. I'm just going to put in here a question mark, shift. This is what we're after here. We have to figure this out. So we want to see how many trials. We have to work this backwards now, and we have to see how many trials it takes so that we get 9 or more calls in a day. 91% chance that is, okay? All right. So if we're going to do 8, okay? So remember we have to do the 1 minus part. If you go back to our formula here, it says we have 8 in there, okay? So it doesn't make sense that we're going to run this test on anything but greater than 8 tests, all right? 8 trials. Obviously, you're going to get this blow up on us until we get down to here where we say, let's run 8 trials and see the probability of 0 to 8, the summation of that. What's the probability of that? Okay, so let's get this out of here. Okay, so I'm going to hit escape, and I'm actually going to grab it up in here, control exit. I'm going to exit, and I'm going to drop it down. The first number of trials that makes sense is to drop it into here. Okay, let's see what's going on there. It should work. It should be C17. Oh, okay, so we just have to fix it there. Okay, you just have to update this cell reference to C17. Okay. All right. So the probability in 8 tests, okay, so we do 8 tests, it's 0 probability that we're going to get 9, right? That makes kind of sense, right? Because we haven't hit 9 yet. We haven't even found them yet. But there's another reason for that, okay? So remember, we're trying to use this left-hand part, the summation part of the formula on this. Let's just see what happens, okay? So it's 0% chance that we're going to get the result that we want by running 8 tests. Okay. Now I'm thinking we're going to have to go pretty deep into this. We're going to have to run a number of tests. Why? Okay. Before I go even further than that, well, we know that it's probability of only 7 out of 100, right? So 7 out of 100 times we get anything. So we're going to have to at least go to 100. Let's drop our numbers to 200. Okay. So we have to go more than 200. I'm sorry, more than 100. We have to go to about 200. Come on, speed up. Here we go. It takes off. Okay, so whatever we got. 183. Let's try 183. Okay, this is the number of trials we've got to take to see. Remember, because we're doing 1 minus here, that the probability, forget the 1 minus for a second, the probability, in fact, I'll just get rid of it here for a sec. The probability, oops, fix that again. Right. The probability is 100%. I'll tell you that has zeros to infinity on this. This is the probability that the summation of the outcomes of 0 success and 1 success and 2 success and 3 success and 4 success, and we're adding all them up because we're using the true part of the formula there, is equal to 1. Okay, so you can find out here that if you run a binomial like this with these two numbers the same, which they are right now, C17 and 8, you're going to get 100% probability there. Okay. Okay. So remember, these are the numbers of times we're running the test. I'm going to kind of blue them out or something. Let's go here and let's color them blue. Yeah, it's fine. All right. So they're blue. It's a little dark. Do one more time here. Okay, so we'll center them up. Okay. So they're invalid. These are like invalid. You can't run a binomial test here and look for 8 successes in 7 tries. Okay, get it? Okay, but once you get to the 8th one, it says within 8, what is the probability of success? Well, if you add all these probabilities up, it comes up to 100%. Okay, so now I'm going to drop this down. Okay, now one thing I'm going to do is increase the, let's go to 4. How many places is that? Let's go to 4 places there. Okay, so now what we're seeing is what's the probability is going to drop here as we increase the number of trials. Let's go all the way to the end here. Okay. All right. Now what happens here, it goes from 1, and you notice there's just rounding errors in here. I'd have to put out more decimal places, and this would not be 1.0. In fact, let's just do that just to show you. Increase the number of the decimal places here. Boop, 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 boop. You see, we really have an honest 1 at the top. That's 100%. Okay. And then as we have more trials, it opens up area. There's more trials where these outcomes will not add up to all of the outcomes. And that's why this is starting to drop off here. It starts dropping off. Okay. Okay. And so finally it says, what's the probability of only getting 0 the problem of 0 to 7 as an outcome. I'm sorry, 8 out. The probability of getting 0 through 8 goes down because we can get other outcomes in here. Okay, that's why it's decreasing. It decreases as we go down to 183 here because there's other outcomes that can happen. Now, if we put the 1 minus in front of it, like we had started out with, I'm going to redo it with this 1 minus, okay? Because now we want to subtract. What's the leftover probability? There's 0 probability left over, okay, up here that we would get 9 or more. Okay, 9 or more. Remember, we're really looking for 9 or more phone calls in a day. All right, so I'm going to drop this all the way down. I'm going to copy this down. Okay, and what was the question? The question said a 91% chance. Okay, so this is our opportunity, or this is the probability that we're going to get 9 or more. Very, very low here. So we have to look down this table. We just tabulated the values here. Okay, slow, it's a little bit slow here. 91, looking for 91. Oh, we didn't even get there yet. I have to do this 2 different ways. Trials, I did have to go down there a little bit more. How many more trials do we have to do? Let me just copy this down here. So we're looking for the boundary around 91. We were almost there, okay? So the probability of getting 9 or more phone calls, all right, you need to make 181 calls. Well, we only have a 99% chance if we do 181 calls. We're running 182, comes up to 89, a little bit more. We're out into the thousands places, right? And what we're doing is we're looking down here till it finally passes into the 91% mark right here. Okay, so let me throw some orange in there, or yellow even. Yellow's even better. Okay, so that's the number of trials we'd have to take to find 9. Okay, so that's how you handle the problem like that. Might not be too obvious, but that was a little tricky. So that's why I said, well, by now you've seen it. Spoiler alert, right? But the idea was to stop the video and give it a whirl and see if you could figure out how to do that one. Okay, so problem 33, you're going to have to fetch the file, a little document. They sure don't make that little thumbnail there very large for you to see, but I'm going to go get that. Hang on just a second. I'm going to pause for a moment, go get it. Okay, so I went and fetched it. I'm going to put it in up here. I think I might have killed it. No, it did come in. All right. Thought I made too many clicks here. All right, so I just pulled in the file that they reference here, and this is a kind of a 2-part problem. First, they want to have you work through certain basic non-Poisson issues that are going on here. So it's a Poisson problem. I'm not sure they tell you that or not, okay? But this is a Poisson type thing. Yeah, I think they're going to be telling us to use that. So this is more primitive type of calculations to begin with. It ends up feeding us a few more parts of the problem here. So it starts out just doing simple weighted averages of this thing. So it says find the probabilities of 0 to 12 hurricanes each season using these data. Now, as I'm talking here, you can always stop, read, and then continue here. So I'm just kind of reading what I need to speed this up a little bit. Okay, so what are the probabilities of 0 to 12 hurricanes? How do we do that? So this is like a cross tab, if we think about it here. So we're going to figure out what the probabilities are and spell it correctly. Okay, so we have the frequency of 0 is 6, the frequency of 1 is 16. So kind of take a quick look through here. It's kind of weighted to fewer than more, right? So there's more occurring down here at a lower number. So 16 times they only had 1 hurricane wherever this is. Okay. All right, so we need to do the probability of each of these. Okay, so the first thing we need to do is probably figure out what's the total number of readings that we have here. Okay, so that is going to be an alt equals will be a sum on that. So we have 75. Okay, so we have 75 readings that fit in bins, if you will. You could do a histogram of this. Okay, so what's the probability? Okay, so the probability of 0 is how frequently it occurs. It happens 6 times out of 75. All right, so we're going to say 6 divided by 75, and I know I'm going to drag this down, so I'm going to hit it with an F4 there and lock it down. Okay, so I lock down the total sum there. Okay, and then we'll drag this down. Boom. Okay, so we have all these frequencies. Let's clean that up a little bit, and let's go up one. Yeah, like that. It's fine. Even go one more. I'm not sure how many digits it asks for. 3. Okay, so we have three digits there. There's the probability. And so what you would do is you'd go ahead and you would load them into this one by one, and be careful and double check and then hit enter. Okay, so I'll drop that in here. Control V. Okay, so I just punched the numbers in here. Save this a little bit of time. I can just write over that. Okay, great. What's the mean number of hurricanes? This is a simple mean. Okay, so how would we do that? Okay, so the probability times the number that actually occurred is what we're after right now. We're going to weight these. Okay, so 8% of the time there were 6 hurricanes. No, 8% of the time there were 0 hurricanes. 21.3% of the times there were 1. Okay, that's why we use these proportions, which we just described as proportions of allocating each of these numbers of hurricanes per year. Okay, and usually Poisson is what we use when we have a measure of something per something. So we have hurricanes per year here. That's why we're looking at Poisson eventually. Okay, they're just asking us some prelim questions here. So what is the mean? Okay, so let's figure out the mean. And the way that we're going to do that is we're going to take the weighted. Basically, this is the weighted average is what we're after. Okay, so it's 8% times the number of hurricanes. Okay, so 8% of the time we have 6. Okay, so now we can just bring that right down. Okay, and then what we do is add all those up. Okay, and so the average number of hurricanes is not correct there. So now we need to find out what the mean number of hurricanes are. So, or the mean is rather. So the probability times the number is what we're after here. We came up with the probability by the frequency. Okay, so in this box we're going to type equals the frequency times the number. Okay, so that came up with 0 as we would expect. Okay, so then we can just drop this right down. And then going by what the book says, I'm going to clean that up just a bit. Let's see what we get out of that. I'm not sure how many decimal places it says 3, so I'll do that. Okay, and what do we do with that? We add them up. Okay, so I'll have you take a look in the book. It is in there, but we're doing a weighted average. So the numbers that we were fed, it comes up with 2.893 is the average. Okay, so we use the weighted average technique there. Okay, and so I'm going to go punch that in, and I'll be right. Okay, so I punched that in. We got the right number right here. I'm just trying to overlay it in the same place. There we go. Okay, so that was our progress there. Now let's get to the Poisson. And we have besides the reading that we have in the book, we also have a formula coming out of Excel here. So assuming a Poisson distribution using the mean number of hurricanes, which we just came up with, compute the probabilities of experiencing 0 through 12 hurricanes in season. So I'm going to use Poisson, okay, rather than weighted average here. Okay, compare these to your answer to part A. How accurately does a Poisson distribution model this phenomenon? Construct a chart. Okay, so we'll go ahead and do that. All right, so we have to figure out what the Poisson distribution is here. So we're going to do right up here. We'll do. We're just down by 1. Let's type that in there. Poisson. Okay, so it's going to be equal to the Poisson distribution. And what it wants is the x, the number over here, by the mean. And we're going to do cumulative. All right, so I think we're going to do false in there. Let's run false. We want to do false. Okay, so we're going to want to know what's the value? 0. What's the mean? There. Let's put a false in there because we just want to see each bin, what the probability of each bin is. If you put in true, it would as we pull this down, it would go from 0 to 1. Okay, 1 being 1.00 probability. All right, so we're going to run this thing down. Zing. Of course, we have to lock some things in here, right? Lock that in. Now we'll go do it. There. Okay. Let's knock this down to 3. Yeah, it wants 3. Boom. There, we got it. Nope, one more. Okay. So these should vaguely look like the probabilities we came over here. I mean, they should relate to each other about the same. Notice we have some very thin tails at the end here because we have very few high numbers of hurricanes. The high numbers of hurricanes is low. Okay, and they're kind of bunched up in here. And obviously, having 2 hurricanes a season, it happened 20 times. Okay. So we have our Poisson. I'm going to go run and tuck those numbers in there. I'll be right back. Okay, we're back. Put these in here. Okay, so here is our, lay that over there. Start. Okay, so we tucked the numbers in there. We got a thumbs up from the system. Okay, now it wants to say compare the probabilities assuming a Poisson distribution to your answers in part A. See, we already had a probability. Now we have a new probability with Poisson, different kind of distribution. Divide each Poisson probability by its respective probability to get a measure of their relative ratios. Okay, so let's go do that. So what is it? They're telling us to take the Poisson divided by the original probability over here. Okay. So what can we take away from this is, let me get down to 3. There we go. Okay. 3 decimal places. And we're just looking at the size down here. 0.055 is 0.692 of 0.080. So that's just the ratios of these. And so it started out that our Poisson numbers are smaller and then they get larger. Okay. See, the numbers go to 4. We ended up at the middle here. It's overemphasizing the Poisson at the frequency 4 in the table here. It's 4 times as large as the weighted average. Okay. So this is modeling it a little bit differently. Okay. And then it comes back down again until when we get down to here is that since this is a ratio, is that it's much less. These are underemphasized. The tails are underemphasized, and the node, the middle part of it, is overemphasized. Okay, or more highly. Not to put a pejorative spin on it, like stay objective on this thing, is not to be a pejorative. It's just it is much larger. It more highly emphasizes the central numbers than a normal weighted distribution. Right? That's what it was all about. That's what that was about. Let me go punch those in and be back. And that's the answers tucked in there. I'll let you figure out the next part here. This last part is drawing graphs. Okay, so you have to graph your data up here, and I'll leave it up to you to get your graphs. Okay, and then you have to figure out, you have to click which one of these is correct after you graph it on your own. Okay, so that's the first block of assignment 5 or chapter 5. 1, 2, 3, 4, 5, 6. Okay, so we did 6 problems here, and I'll get on to the rest in the second block in the second video. All right, bye for now.